Okay, so this lecture is going to be a bit of a digression, a short digression into some abstraction, groupoids. Okay, so but we'll start with the typical example. So a typical example of a group, remember, is that if I take a space X, then I look at, so group is the homeomorphisms of X. Okay, so this is going to be the set of all f from X to X such that f is invertible. And similarly, I could take V to be a vector space, and in that case I can look at invertible linear maps. This is often written as GL of V. So I look at L mapping V to V. So this is invertible and of course linear. So groups are in some sense an abstraction of this idea. What about, so these are the groups. What about groupoids? Well, that's kind of typical to generalize this in a way. So you can think of these as symmetries, which are invertible transformations from a space to itself. Okay, but how about looking at, take us X to be a space again, and you look at the set of all maps f from U to V with U and V subsets of X, and let's just say open subsets of X and f invertible. So you can think of this as external symmetries or transformations which take U to V. Instead of transforming an object to itself, you transform an object to a different object. Okay, so this is frequently you want to do this, especially if you're looking at, say, biholomorphic functions, because there are very few from the whole space to itself, but there are many on subspaces. Or of course we could look at L from W1 to W2, where W1 and W2 are contained in V are subspaces. And again L is invertible. So this is what we want to capture with groupoids. It's quite central in dynamics and also operator theory, which you want to think of dynamically, where you want to compose things, but you compose things only in a specific way. But unlike an arbitrary category, everything is invertible. And indeed this is how we are going to abstract it. Okay, so let me make a remark. So we can look at homeomorphisms of X. So these are morphisms of category C so objects of, well, let's call it C. Objects of C is just a singleton set X. And how about morphisms of C? So morphisms of XX is all what I have to say. This is just homeomorphisms. This is going to be f from X to X continuous, which is a morphism, but also f is invertible. So this is a subcategory, but a tiny subcategory of topological spaces. Okay, so groups can be looked at this way, and the nice thing is there's a completely abstract version of this construction, which is what we'll do to abstract the notion of groupoids. Okay, so this is the abstract version. So let's fix G as a group, and then we'll look at a category C, category. Maybe I should call it C sub G or something like that, with objects of C is a single L object. Let's just call it star. I could call it G or something, but that's more confusing. Okay, and then morphisms. Now we only have to say what are the morphisms from star to star. They're G. This is abstract definition of a category. You notice that you have morphisms and of course composition. Yeah, so composition is group multiplication. So we have objects, we have morphisms, and we have a composition, and it's easy to say there's an identity, namely the identity of the group, and this is a category. I mean, it's good to see this example because one tends to think of morphisms as categories as maps in some sense, but you have to realize they need not be maps. It's a completely abstract of structure which has to have some internal consistency. Okay, so far so good, but this is special. So CG is special. There are various ways in which it's special. We'll single out them. First of all, it is what is called a small category. This is technical but important. Okay, namely objects and morphisms are sets. Now you must be knowing from paradoxes due to Cantor and Russell and others that the space of, say, the category of topological spaces, the objects cannot be regarded as a set. You don't have a set of all topological spaces or a set of sets, etc., etc. So this is, on the other hand, there are operations we want to do when we deal with groups which involve this, taking the power set implicitly or explicitly, which you can't do unless you have a set. So this is a technical point which is important, but let's focus on the main things. So you don't have too many objects and categories, but here you have two key points. One is that every morphism is invertible. Okay, this is your first point. And the second point is objects of C is singleton. So it's not only a set, but it's a set with just one element. Okay, so assuming we are dealing with small categories, let's look at these two properties. So these are key properties of, so every morphism is invertible and objects of C is a singleton. Now suppose we drop the condition that every morphism is invertible, then you get monoids. I mean, you can do the same construction with a monoid, this condition goes away. Okay, and I'll say in a moment what I mean by what you get when you drop things. Okay, so given such a category, so suppose I have a category, then in an appropriate sense of equality, so given such a category C is CG, where G is in fact morphisms of star star. Star star is the unique object. Okay, so this thing is fully reversible, the construction. Suppose I'm given a small category where every morphism is invertible and objects are a singleton. So let's say it's going to be called star. Then I look at morphisms from star to star. They have an operation which is composition, and its composition is associative. So you have these conditions, and if every morphism is invertible, you have a group. You always have an identity because there must be an identity morphism. So if I didn't have condition 2, I would get a monoid. Now what if I had condition 2 but I don't have condition 3? That is in fact our old friend the groupoid. Okay, so we'll see explicitly how the groupoids we have give you this kind of category. Okay, so that will be the next. So formally we can define groupoid as simply a small category where every morphism is invertible. As an example, let me look at our vector spaces. Example is we looked at the set of all maps L from W1 to W2, such that W1, W2 are contained in V and L was invertible. So these this set of map we can just take objects of C. So this is a groupoid. More precisely, this is the set of morphisms of a groupoid. Okay, where objects of C are going to be simply the set of all W in V subspace. And morphisms from W1 to W2 are going to be L mapping W1 to W2. No surprise there. But remember, we have to restrict to L invertible. I have not written linear. It's clear when I'm dealing with vector spaces that I want to talk about linear transformations. Otherwise, I would just be dealing with set. So this makes this into a groupoid. Okay, so this is the first example we have. You can very similarly make the example for spaces. Their subspaces or open subsets of X would be the objects, and morphisms would be invertible maps. So they are homeomorphisms between different open subsets. Okay, and the second example, which is much more interesting to us and in general more interesting, is let's take X again as a topological space, but I'm not going to look at subspaces. Okay, and let's take remember pi 1 of X with respect to P and Q. This was actually the omega of X P Q, the space of paths from P to Q, up to an equivalence relation. Okay, so define a category. So you define C by objects, let me put a subscript X or something like that. Objects of Cx are X, and this is of course as a set. It's a small category. We forget the topology. And morphisms So if I look at morphisms from P to Q, remember P and Q are of course just points in X. So this is in X, this is in X. We look at them as pi 1 of X PQ. That is, they are not paths but equivalence classes of paths. Okay, so this is the equivalence class of path, so where alpha belongs to omega of X semicolon P comma Q. And what we showed last time is exactly that. So I have to tell you how to compose morphisms. So composition is just star. Okay, so this is what is called a fundamental groupoid. We'll see this again in the sense that we will use much more when we define fundamental group in the next lecture. But for now, fundamental groupoid, the point is the properties that we spent some effort showing, that star is associative up to homotopy, tells you composition is associative. Similarly, the fact that we have these identities, EP is going to be the identity morphism. So EP is going to be in morphism of PP. This will play the role of the identity morphism. Play the role in the sense that it satisfies the property that identity composed with any given morphism starting at P is going to be the morphism itself. And similarly, when you end at P, you post compose with identity, you will get these. So this star is going to be the composition, EP is going to be the identity. So this will give you a fundamental groupoid. By the way, I have to give a warning, because function composition is written the opposite way to how we write star. Sometimes you have to flip things around, because this is deeply embedded historically in mathematics, that function composition is written in a way that is opposite to what one would normally write for operations. So with the caveat that you may have to clean this up, since we don't deal with this in details, I can ignore that detail. You may have to clean it up to allow for that. This gives you a very nice category. So your space itself is a category, the objects are points, and a morphism is a path. It's a way of going from here to here, only if you do it up to homotopy or do something more sophisticated. Okay, but for our present purposes. So this is a fundamental groupoid. It will be a functor, it will be nice. The fundamental group will build from that. So this takes us to, gives us some nice examples of groupoids, and it's a nice structure to see. It's important. One particular aspect of this is important, which is what we will turn to finally. Namely, suppose we only knew the morphisms of the groupoids, right? So that is, in a group you just have elements that you can multiply. Here you have elements that you can multiply with the condition that sometimes you can multiply them. Okay, so let me try to do this directly. Oops, I'm sorry, I will have to create a new. Let me do this directly. Suppose we have, so here is the main question. So we want to revive category from so morphisms or whatever. And star. Okay, so for example, you just had paths or linear transformations and appropriate ones. So they have to satisfy the appropriate properties. So I just want to point out the main idea, which is important in many contexts. Suppose we were just given a set. We want to think of it as an algebraic object with some appropriate star associative. It's an associative operation. It has appropriate identities, inverses. Okay, so star, and if you wish, we don't even need the bar for this. Okay, but you have a bar operation which satisfies appropriate compatibility conditions, etc., etc. Can we recover the category? That is, how do we get the objects of C? Well, the idea is that, if you remember, in a group, identity is unique. In a group, okay, identity is unique, and indeed it is characterized by the idempotence property. It's characterized by E squared equals E. And the first thing almost you will see in algebra is how this is something satisfying E squared equals E is going to be unique in a group. Yeah. So on the other hand, in our cases we had many other elements which were kind of like the identities, which were constant paths. Okay. So in a groupoid, that is, if I had a multiplication which satisfied appropriate algebraic properties, you can define objects of C, or maybe I should say rather than in a groupoid, let's say we are given a groupoid. We are given a groupoid. We define objects of the category C as being the set of all E, okay, so with elements. So the elements are like the elements of a group. Let me say whatever I'll call it, again I'll call it G. So E in G such that E star E is defined and E star E equals C. Okay, because this is the first case I've emphasized this. When you write an equality in a groupoid, it means they're defined and they're equal to E. Okay, so we look at the idempotent elements. In our case of fundamental groupoid, these will be the constant paths. In the case of the linear transformation examples, they will be identities on subspaces, or in homeomorphisms, there will be identities on open subsets. So you can see that you can recover the objects purely from the algebraic structure. Okay, and similarly, if you are given two idempotents, okay, so suppose I want to look at E1 and E2. So these are objects, they are idempotents. So then you look at the set of all elements in G such that E1 star G and E2, sorry, not E2 star G, G star E2 are defined, and E1 star G equals E1 and G star E2 is G. By the way, the latter will happen automatically if I are defined from the properties of idempotence. Okay, so the point I wanted to make is that just the elements that you multiply, which is the paths, from those you can recover the endpoints. So if you want to define groupoid algebraically, from that you can get the categorical definition, and the same is true even for groups. Groups we already saw, the groups it is even more elementary. Okay, so this is an interesting structure, groupoid. It's important in many contexts, but at the level of this course you should regard this as a digression. We have seen the fundamental groupoid. We'll soon see the group. Really the only role of groupoids here is that it avoids having to prove theorems more than once. We'll just prove them in the groupoid case and specialize rather than generalize to fundamental group. Okay, but the last comment I will make here as far as these things is that from a group, so you can get a groupoid. Actually, sorry, from a groupoid you can get a group. From a group you get a groupoid, of course, which group itself is a groupoid. But from a groupoid you get a group if I am given an object. Okay, so given X in objects of C, which I will think of as a base point. Namely, you look at G as morphisms from X to X. Okay, this is exactly in the case of fundamental groups, looking at all paths and specializing to loops. So that is part of a general construction. As we go along, we'll look at this for the sake of perspective and a bit of culture. Okay, but next we will move away from groupoids to something more concrete, which is the fundamental group.